Okay, so hello everyone and welcome to another 3DOptix webinar. This is the first time that we're doing a live session for Far East time zone, Japan time zone, China, Australia, India. So I hope we'll get good feedback and we'll continue with this tradition. So today it's going to be a unique webinar. It's going to cover 3 topics. I'm going to show you a few new features that we have released in the last couple of months. And it will take me about 10 minutes to show you about these fascinating new capabilities. Then I'm going to segue to Alon Geller. He is an optical designer. He's going to cover beam steering and cover one of the use cases that you can find on our website. And he will show you how you simulate properly beam steering. And the theme of that is how you need to save cost and money. So if you simulate before you actually build it, you can forecast and see a lot of the problems that you will see in terms of degrees of freedom, in terms of the right hardware that you need to purchase. And if you do it before you go to the lab, before you go and build the prototype, you actually save a lot of time and money. This is true for the industry when you build a product, and it's also true for the academy when you want to build an experiment. And lastly, we're going to have a customer case study. This is from MIT. They have used 3DOptix for the past 3 years to build one of their innovative experiment that was later on published in Nature. And Yong-Hoo is a postdoc over there. He's going to present there. So without further ado, let me start. Okay, so the first thing that I wanted to show you is, so about 3 or 4 months ago, we released what we called 8 different example to push the innovative in 3DOptix and to show a new example and what are the new capabilities. They are accessible for users from here, help exclusive capabilities, or if you're a free user, you'll have the letter P, professional, over here, and you'll get the same banner. And in the banner, you would see those examples that you can scroll between of them. And if any of those examples you want to explore that, all you need is press this red link, and it will automatically be copied to your personal directory with all the data. You don't even need to initially do any simulation because the data is there. If you want to do modifications, so this now resides under your personal directory, so you can do all the modification. So you can see, I copied this, now it's yours. You can do any modification. All the analysis information is already there, the initial one, but if you want to make changes and you want to run a simulation then to test it out, so you can do that, that's not a problem. So that's the first thing that I wanted to show you. The second thing that I wanted to show you is polarization. So here one of the example is a source which is polarized. So you can see this is an elliptical polarized source. So this is an elliptical polarized source, and we have here 2 mirrors. So what we have released is on top is what we call polarization analyzer. So when you press this, you see here the yellow banner, pick ray in scene. You press that, and now you need to select one of the rays. Let's select this one. And then you need to open this, and then it says pick a point in the ray. So now I can select a point, and you can see immediately the polarization direction. And you can add another point. So let's add another point, and then add another point here, for example. So you can see the polarization across each and every segment. If you open one of those segments, there is additional information for that specific segment. You can actually, this is point number 1. So you can move this. Let's do 160. And, we move that because this is the same right here. Let's do 1. So here, 160. You can play with each and every direction of the polarization. And there is more information, and you can have that information for each and every spot or dot that I've selected. This feature, by the way, is available for our premium user as well as in our 14-day free trial. So this is something very useful. So that is polarization. The next feature, which is Coherent Manager. So I'll move to another setup. Okay. So I have this setup. So I have 2 sources, and each and every one of them is, as you can see, it's plane wave, standard one, the default 550. And when you open the analysis, so we'll give it a second. So you can see that those 2 sources are not interference. There is no interference right now because they're not in the same group. So what I would need to do in order to make that available, so I would go to the Coherent Manager, and now you can see the 2 sources. This is the first one, LS5 and LS4. And I would just pick a name of type a number of a group. So let's put them in 1. So now they're on the same group. And now I would run the same analysis. So now, as both of them are part of the same group, so now you would see the interference and the coherence. So we'll give it a second. Now we can see completely different results where the 2 sources are interfering with each other. And this is what we call a coherence manager. So that's the next one. The third one that I wanted to show you is what we called 2D sketch. Now, a few years ago, we had a similar feature, which we eliminate, and now we bring in a more, I would say, nice fashion. So for each and every design that you have that involves mechanics and optomechanics, you have the ability to remove layers for presentation, and then you can print that out. And people are starting to use that as a 2D sketch tool. So how it is done. So you can see this new button. This is show hide parts. And you have different layers. So there is coordinate system, optics, light source detectors, and optomechanics. So we have here, this is an interferometer, a Mach-Zehnder interferometer. Most, if not all of the parts here are coming from Edelman Optics. But now you want to do 2D sketch. So the first thing that you do ideally the optomechanics. We do have here camera view where you can play with the view, or just leave the isometric view and just rotate it. So now you can zoom in. Let's delete this. And all you need to do is go, and then you can download an image. If you're a premium user, you can go to the higher definitions. If you're a free user, so this is the only thing that's available for you, the high definition. So this is very nice. By the way, you can remove all the other layers, the light source, the detector, the optics. Another nice feature, by the way, here is that you can go and change the ray color palette. So for example, you can do directional, wait a few seconds, and then you'll get different colors. You can change the background by going to user settings, go to setup relate, sorry, to global. Where is that? Just a second. Here, view settings, I'm sorry. And you can change the background scene. You can change it to any color that you want. Let's do it a little bit more reddish. You need to save that. And you can play with that as well. So let me just bring back the background because I do not like this. Okay, so that is the 2D sketch. In addition, let me go back over here. We added in the user-defined object more features, so let's open that. Again, all of those features are available for our premium users, and they're also available in the trial 2 weeks period. So if you go and select masks and then images, so we added a lot of more presets. So there are grading presets. They're going to be updated in a second. So there are a lot of more new masks over here. Let's go back. Let's go back. I think the nicest ones are pictures, and they're very nice pictures that you can select. And if you import that, a specific one, and so you can see, and you'll have that already in your screen. Okay, so that was that. The last thing that I wanted to mention is we added a lot of more advanced simulation. They are going to be here, so you can try them out. Okay, so that's my part. And now, without further ado, I'm going to segue to Alon Geller. He's an optical designer. So let me do that and share it with you. So wait a second.
Thank you, Gil. My name is Alon Geller. I'm an optical designer working with 3DOptix. 3DOptix is a great digital optics platform that allows you to prototype your concept before building it, before ordering parts. It allows you to build a digital twin of your idea before building the lab setup or prototype or your production model. It allows you to save time, save money, make sure all your parts fit before ordering them, whether they're off-the-shelf parts or custom products. 3DOptix allows you complete optics simulation in 3D. It has a catalog of over 45,000 off-the-shelf parts from companies like Thorlabs, Edmund, and other major manufacturers. Today, we're going to be going over a laser steering system. We have two different systems we'll prototype here. The first is a static steering system with two fold mirrors. This allows us complete control over the position and the angle of the laser beam. And the second is a dynamic system with two galvanometers. This is useful for scanning the laser for systems such as 3D printing, LiDAR, and any other application where you need to scan through a laser beam. So let's jump in. Back, there we go. So this is the 3DOptix platform here. On the left, we have detectors, sources, and here's the product catalog where we could add in many different off-the-shelf optics and mechanics. So as we said, we're gonna first create a static steering system. So we'll start with a source, drag our source in. We could click on this. We could position it where we want, put it in the center of our coordinate system, and we'll keep it 100 millimeters up to allow us to place mechanics under it. There we go. Once we have our source where we want it, we adjust the source properties on the right here, like source settings. Go down, we'll make this 5 millimeters. So we'll change the wavelength to 633 nanometers. Helium neon laser. Here we're able to put in many different wavelengths at different weightings, create different broadband sources, also have a catalog of different sources. Now that we have our source, we'll add in our beam steering mirrors. We'll take this from the catalog. We're going to use a 1-inch Thorlab or 20 millimeter Thorlab mirror. We know the product number. Here we go. See this. Here we go. Add this mirror to our design. Once we have our mirror in place, we can position it to where we want. We're going to put it in 200 millimeters from our beam. We're going to tilt it 22.5 degrees, which will allow us to have a 45-degree angle. Then we'll add a second mirror in, and this will give us what's called a figure 4 configuration, which is a nice compact configuration that allows us complete control of the beam steering. Once we have our first mirror, we can duplicate that. Rename this. Mirror 2. Save that. Change its position. We're going to put this guy at 100 millimeters out. And this should allow us to see a 45 millimeter tilt. Sure. There we go. And we can check this by doing a propagation simulation. This traces rays, the system's allocating processing power. 3DOptix is great because it's entirely cloud-based. It doesn't depend on your processor. Everything is on the cloud, and once it allocates the necessary processing power on the cloud, it's quick. It allows you to trace millions of rays in a very small amount of time. Go in a second, it'll come up. And we'll be able to make sure that our mirrors are placed accurately. And this will position, the detectors have a front and a back. If you zoom in, you can see the front. And from the other side, has a little B for the back. Position this. Now we got the detector in our beam path. Such, and we can simulate this by going here to the analysis portal. Right. This is our this is the detector that's available with the free version. The more detailed detector allows us to increase our pixel count. There are many other detectors available for coherent illumination. Run our analysis here, and we should see our 5 millimeter spot on the detector. Again, it's allocating system memory and positioning the different objects. And here we go. We click on our detector and we see our spot. We're able to move the cursor around, see the intensity, see the color map here, and see the positions as well. So that's a basic figure 4 configuration with 2 static mirrors. We could tilt these to adjust it. And the next simulation we're going to do is with 2 galvanometers. So this, there we go. There we go. So again, we'll add in a light source here. Position it where we want. Move this over a little bit. Yeah. And again, we'll increase the size. Here. Again, we'll make this 5 millimeters. We'll make the wavelength 633. Excellent. Okay, so now we got a second light source here. And the next system we're going to do, instead of positioning each one in space, we're going to position each item relative to the previous item, which is a really useful feature of 3DOptix. It allows us to build up complex 3D models without having to know the full 3D location. Each object could be positioned with respect to the previous object in the chain. So once we have our light source, we'll take the galvanometer from Thorlab's website. Here we can see GBS 111, the 10 millimeter galvo system, and here we can see the step file. We can download the step file, and then we can go back to our 3DOptix and we can import. We can right click, import CAD, auto mechanics, and then we have our GBS 111 step file. Click OK, click import. So it imports pretty quickly. There we go. Get the detector. Again, we can first drag it over. And what we're going to want to do is we can see that the coordinate system here is at the bottom of the part. But actually what we want is we want the coordinate system to be on the mirror, right? So 3DOptix allows us to do that. We can click on the part. We can click on add coordinate system. And now we're able to choose a point on this 3D part. So we choose a point that's off to the side of the mirror. Click on that. And then 3DOptix asks us to add an x-axis and a y-axis. So for the x-axis, we're going to choose this line, edge. There we go. The y-axis is going to be this line. And we can set it as the local coordinate system. This means that when we position this object, it'll position in reference to this coordinate system here. There we go. So once we have that set, we could move and rotate the part. We're going to position it relative to this relative to our source. So we click on this here to pick a reference coordinate system. We pick our reference coordinate system, and then we're going to position it here. 0 x, -8 millimeters to account for to put it in the center of the mirror. And we're going to put it at a distance of 200 millimeters. We're going to bend it at 45 degrees, which will give us a 90-degree tilt. There we go. We should have our beam in the path. And again, we can test it by running the propagation simulation. We should see this beam hit the center of the mirror. Again, it's positioning this object. Once it does that, it runs pretty quickly. Perfect. Okay, so we could also unclick the first one and run just the source that we want. So we'll see that the laser hits this mirror, but it doesn't bounce off the mirror. It's absorbed by the mirror. And the way we change that is by changing the properties of the face. So again, we right click here. We could go to CAD settings, choose face to determine its properties. Then we're going to want to click on our mirror face. And here we have the option of changing the optical properties of this face. We're able to choose absorber, reflector, some fraction thereof. And we're also able to choose scattering info. We have a full array of scattering possibilities, scattering models. The moment we'll leave that off, and we'll set this as the ideal reflector. So now when we run through the propagation simulation, we should see this beam bouncing off that mirror, the 90 degree. There we go. Once we have that down, we can copy this, duplicate, and this will copy our coordinate system as well, which is quite nice. The next thing we're going to want to do is we're going to want to position this with respect to the first galvo. However, the first galvo, we see our coordinate system is at 45 degrees, right? Aligned with the mirror, which is good for positioning the galvo itself, but it's not so good if we want to follow along the beam path. So what we're going to want to do is create a second coordinate system. And we're going to rotate that 45 degrees with respect to the coordinate system of this object. We right click, we click add coordinate system. Second. So add coordinate system. Here we go. And here we rotate again, we're going to set it relative to this coordinate system, the same location, and we're just going to rotate it 45 degrees. And there we have it, right? Rotated 45 degrees. So once we have this rotated coordinate system, now we could position our second galvo relative to this rotated coordinate system, which will align it in the path that the beam goes. Right, so again, here we're going to choose this new coordinate system that we just positioned, and we're going to align it relative to that. Sometimes these positionings are a little bit complex, but what's nice is as we change things, it changes in real time. So we're able to see where things are in real time, right? Click our new coordinate system here. There we go. There we go. So now we're able to see. Millimeters is right. We're able to see in real time in relation to this other galvo and in relation to our whole system. So now we're going to tilt it to move our beam coming up. And that should reflect our beam coming up. And again, the optics properties of the surface should be saved. We can see here that our beam is going through the center of the face, which is what we want. And let's run our propagation simulation to make sure that it's reflected in the direction we want. Awesome. So now we see we have two 90-degree bends, which allows us for a full sweep in 2 dimensions, right? This will be the X and the Y, allows us a full sweep. The last step is we're gonna put a detector. Add that in. And here, we're gonna use another neat trick about 3D optics. Instead of positioning it relative to one of the coordinate systems, we're going to snap to chief ray. And here, when it turns into a plus sign, it'll snap the detector into the center of the beam, right? So we don't need to worry about the positioning in X, Y. The only thing we need to do is to rotate this. Here, we'll just clean this up. Here, we'll put it 0, so the lens is, the detector is square to our beam rotation to our system. And there we have it. Now we have the beam in the center of the, the detector in the center of the beam, and it's fully positioned with respect to our galvo system. And now we can see, we could do the same analysis that we did before. So here we're going to look at only the second detector, right? We're going to change this as we did before. We don't need our first source. We're only looking at rates from our second source. Increase the pixels. Run our analysis. Again, position the object, allocate computing power. We should again see our beam in the center. And then we can see what happens when we begin to rotate our galvo exactly. So here is the beam in the center. And now we can see what happens when we begin to rotate the galvo. So here's a 2-degree rotation. Run our analysis again. There we go. We can see our spot has moved. We can also see here that the beam has moved. Now this beam is not going to be, this beam is going to move as a function of the tangent of the angle, meaning a small angle that's going to move a little bit, and as we increase this angle more, it's going to move more and more. The next step we're going to do is we're going to add in a lens between the galvo and the detector, which will simulate an F theta lens. An F theta lens will allow us, instead of moving with the tangent of the angle, it'll allow us to translate directly between the angle, the theta, and the position on the detector, which is why it's F theta projected instead of F tan theta. So we'll add in here a paraxial lens, which is an ideal lens. Okay. Add paraxial lens. We'll position this guy exactly halfway between our detector and our scan mirror. Turn this. There we go. So now when we run our propagation, we should see our beam focused on the detector. Sorry, right. Of course, we have to change the focal length of the lens. Come over here to the optics properties. Paraxial lens settings, right? We want to change the focal length. 50 millimeters. There we go. Now the lens, now the beam should be focused on the detector. And I was changing it, sorry. Millimeter, there we go, EFL, plus. There we go. There we go. There we go. Now we can see that our lens focuses nicely down onto the detector. We change the side back to what it was. There we go. And now we see that as we scan through, right, the beam remains focused on the detector. So we'll go back to 0 degrees here. The beam will focus in the center of the detector. And we can see this in our propagation simulation. When we run our analysis, the beam is going to be centered to the center. Focus to the center. There we go. See, it's a nice small spot in the center there. And as we move off axis, move 2 degrees off axis again, 37. We rerun our propagation simulation. And we'll see that the beam moves over in proportion to the tilt of the galvo. At least for an ideal data lens. There we go. See, the beam has moved over. That's our presentation for today. We went over a number of different positioning schemes, both as far as with respect to the local coordinate system, with respect to an external coordinate system, snapping to the chief ray, which is a really nice feature. We went over a static steering system, a dynamic steering system, and you can see how you can bring in external elements from CAD, from the different optics catalogs, different lenses, and fully build up a system and simulate it before you order your parts. And that's our presentation for today. Thank you very much.
Okay, thank you, Alan. Now we are going to move to our last section. I'm going to segue to Yong Hu from MIT. You see there are a couple of questions. So I hear that there is some background noise. I'll try to improve that.
Thank you, Gil, for inviting me to give this talk about sharing my experience for using 3DOptix in my research. I'm Yong Hu, a postdoc associate from Professor Kingland's lab at MIT. At our lab, we focus on quantum photonics based on solid-state data centers. Here, we have been actively using 3DOptix for the past 1 to 2 years for digitize our optics setups. As you see from here, it's one very complex setup from lab, which was used for recent publication in Nature, led by Linson. This setup, you can see, it's actually a little complicated for new users because it involves 5 systems, it involves cryogenics setups, also a lot of detectors, and EM60s, also different lasers. The successful implements are based on how you can accurately align and optimize setup. So the most challenging one for me when I reach to this step when I come to lab is A lot of element is, for example, lens was actually mounted. So if you don't label it well, you actually don't know what is inside this lens. In the future, it will make you hard to understand how you can optimize and even understand why people put this lens. So this setup, as you see here, the photos, it took actually a few people's at least 3 years experience to gradually update and improve it. So as you see from here, if a new user like a new lab members go here, it will be a little hard for him to tell which lens it is and why people put it here. Even you have the diagram for the optics. That's make us want to design a digital twin. And then we start collaborate with 3DOptix. We actually made the distance and get the CAD files and optical elements by collaborating with the 3DOptix to digitize all setups. With this now, you actually can view and even see the optical performance of the optical elements by just simply click it. And what's good is that you can actually copy and share this setup to all the new users in the lab, where they can just not use the setup, but still can play with the setup, change the optic element, and even provide some novel suggestions how to improve it based on their previous lab experience. Okay, so another thing is actually, as you can see, the powerful, which I think is the only platform which can digitize the optical setup in the lab. The other things which I feel very useful other than all the advanced analysis technology is the bill of materials, which actually when you build the element, it's not just the CAD file, it's actually provide the model numbers and even link to all the company. For example, here's the example, the PBS, beam splitters, which is you can directly click it and find where it's beam split and audit if you want change it or you want to use it for our setup. So from my experience is that other than, as mentioned, other than all the technology part, all the advanced analysis which will help you understand optics better, do the better analysis, the direct tool experience for me is it saves the cost and saves the money for me and our lab. So let me go into details. So as mentioned that usually this complex setup took a few people's effort, and the lab usually this kind of setup shared by maybe 4 or 5 people. And usually an equipment will take 1 week or even longer. So it means that a lot of users don't have the time, actually spend time to just align optics and change optics in real time. So when people actually have this setup, my friend said we can have a meeting in the office and play with the setup and see how you can actually figure out the issue with setup and improve setup based on the design. Then when you have everything digitized, it only takes you a few minutes other than 1 day to align everything and even change the design. Also, it will be very beneficial for new users, where you can actually discuss with some experienced people who have been in the lab for a long time, and they will train you and understand you what looks like. It has been shown that new users feel very helpful when they see the screen, other than just look at these photos as you can see. And other things I think will be also very valuable is it saves the money. It has a lot of aspects. For example, the time is very important, right? A lot of people get paid and they want to save money for their research, not just other things. So when I have twins, actually it helps people discuss efficiently and save the people, leave the more of time in the setup for the real equipment. Secondly, is I think is because it has this bill of materials, which means that you can simply just took a few seconds to order parts you want. It means that usually when a lab will become big, or we have new ideas and new money by new equipment, you really want to copy this existing setup and do some improvement. So original way, like, it's really hard because a lot of people don't save all the document when and where, how to buy the parts for the setup, not other than where you place the setup. But when you have this tutoring, actually, my opinion is like you only need to take a few minutes to order all the parts from the vendors, because this all the information can be sold in the bill of materials by simple click. It means that you can very confident to know how to copy a setup, even you are a new user, because you are only look at DigiTwins, look at the position and use the ruler and know some basic optics. That's why I think that's my experience about 3DOptix. It actually my experience that from a non-optic guys into some kind of familiar with setup. It took me like 1 year to familiar with setup, but until 3DOptix, it took me just like 2 months as I gradually involved to build the twins to understand all this essential part. For example, the 4F, how the gavel was placed, how line beams, how you this field will change your collecting efficiency. I was so benefited by 3DOptix. That's why I want to share with all of you us if you got a chance to try it. Finally, I want to thank Gil for inviting this talk, and also for all teams in 3DOptix, Professor Ham, Dr. Asfa, and Dr. Romer, and also team at MIT. Thanks, Professor England, for support this, and thanks to Dr. Siwan and Jules Linson and Kevin for all the effort on this setup and DigiTwin. Now I give back this to Gil. Thanks.
Thank you, Yong. Thank you very much.
Okay, so thank you very much, Yong. I will now open up Q&A if you have anything for the presentation that we have seen right now. So if you have anything to ask, just put it in the Q&A form, and I'll try to answer this right now. So let's give it a try. By the way, if you do have not just question, you have any suggestions for future webinars that you would like to hear, any suggestions or feedback on the software itself, that would be very beneficial for us, and I believe it will help growing the community. So feel free to do that as well. So the question that I got, is it possible to analyze interference pattern of two laser beam arms? And the answer is, of course, yes. I believe we have in the example, and I'll show you that in a second, a Mach-Zehnder interferometers with two identical arms, where you are trying to measure the index of refraction. So let me just open that design and share it with you just to show you. So I guess you were referring to this. So we have one source, two identical arm. And if you want to measure the interference with the same source, of course, you can do that. You can see here. So let's go to this. So you can see here the interference that you're getting. Just to show you, we will tilt this. This is 45 degrees. We'll do it 45.01. And then we will run this again. And then you will see how the interference here would be tilted. And then there is another way of showing that by changing the width of the window. So you can see that immediately. So let's just, give this back. And another way of doing that is by going to the setting of that window. And then there is here the thickness, and we can change the thickness like this. What will happen, we'll try it again, and then you will see that we change the thickness of that specific element, and then it will change the interference. Now, if you have two different light sources, then you need to group them with the coherence manager, and then you will be able to see the interference of those two separate light sources. So over here, now if we zoom in, you'd see the change here in the fringes. It used to be half a pi with the 0.0008, and now it's a little bit shifted. So the answer is yes. Is shear plate available with the catalog and interference pattern on it to observe? So if you're, I'm not sure exactly what you mean, but if you can send this email, and I'll try to get back to you offline with that. But on the catalog, we have about 45,000 optical elements. So you need to go to the catalog and see if you find the pattern that you are looking over there. If that is not available for you, so when I say catalog, I mean you can go to the catalog from this button, or right click, and then you open the catalog. So the catalog has, in the optics section, all these types, and for each of these types, there are subtypes. So for example, if you're looking for a mask, so you cannot, so this is just one. If you look for a lens, so you have all these options. Now, if you right click and you can create one with the user defined, so this is what I said, this is where you can create your own elements. So you can select one of these in the mask, and these are available. And as I showed you here from the, so those are the presets that are available. If those, you don't find what you're looking for, again, you can upload any custom file with these preferences. I hope that answered your question. So I'm getting a link. So there is a link that I got. So, okay. So in this case, you can simply build that. We don't have that specific element in our catalog. I can see that it is composed out of off-the-shelf component that where you can build them by yourself. So that specific element is not part of the catalog, but as I showed you, you can simply build this in 3DOptix. Any other questions? If you want to have, like, you have a specific use case and you want to talk with us, and you're interested in purchasing a license and you want to see a demo first, that's not a problem. Just send us an email to info@3doptix.com or support@3doptix.com, and we will set up a dedicated demo with your own use case and to see if we can meet your exact needs. Most of the cases, the answer would be yes. And I'm sure that you will face very serviceable people that can help you solve your problem. So thank you very much for all of you for attending. And thank you very much for spending the last hour with us. So this recording will be available on our website next week with all the other recordings. So thank you very much and have a great day, or for you, a great evening.